Hi, Paul. Hi, Rob.
Hello.
Here we go.
Hi, Nick. Hi, Rob.
Hello. how to run one of our
Thanks to everyone who's joining the call. We are due to start in about 5 minutes, so please bear with us as more people log in and join. If you're just joining us, thank you for taking the time to join the webinar. We are due to start in about 3 minutes, so more people are currently joining, and we'll give it a bit more time before we get started. Hello, good afternoon, and thank you for joining the webinar. We will give it a little bit more time before we get started. We've still got participants joining. Perhaps give it another minute, and then we'll begin. Good afternoon to everyone who's joined us today. We will get started now, and yeah, I'd very much appreciate your taking the time out of your day to join this session, in which is the seventh in a series of sessions that we've been running with CBSE over the past 6 to 9 months. So for many of you, this may be number 7. You may have dived into various events that we've run previously, but you will. This will work as a standalone session, but you can also, and I'll talk about this a bit later, access recordings of previous events that we've run through the community website where you signed up for this one. So before we get started on this final webinar in the series, which is focused on how to bring together your learning from the previous sessions and your practice and experience, and to implement that within a competition for your students. Before we get started, I would just like to thank CBSE, in particular Dr. Saha and Mr. RP Singh, for the opportunity to work with them on this series of webinars. We've very much enjoyed it, and we're looking forward to this final one. So let's get started. Now, the order of events for this one is going to be very similar to previous ones. We'll start with an introduction to the Arms School program. We'll go through that at a reasonable pace, just showing you where you can find further information, where you can download resources and projects that relate to the session today. And we will then move on to the main professional development session, which is will be run by my colleague Rob Lehman, who will introduce himself in a second. And before then moving on to feedback, my colleague Surya will say a few words about providing feedback on today's session. We'll then do a Q&A, probably about 10 or 15 minutes, answering any questions that have come up that Surya has been unable to address throughout the course of the session, before we then move on to closure. So on questions and answers, I would ask that if you do have a question, that you put it in the Q&A box so that we can keep track of that as they come up, and we'll address all of those either as the session progresses, which my colleague Surya will do, or within the Q&A session towards the end of today's event. A few other housekeeping points. So certificates, this is a question that frequently comes up within the sessions. How do I get my certificate? The answer to that is it will be emailed to you along with a link to a recording of this session after the event. So that will come to you because you are registered for this event. So we have your details and we can send that on to you. And within that email, there will be the PowerPoint deck as well. So all that information will be sent through to you directly after the event. Okay, let's get started. So first of all, just an introduction to your speakers. So I'm there on the right. My colleague Rob Lehman is there on the left, and between us, we work across the ARM School program and the apprenticeship program. And we both come from an education background, and Rob in particular has got a deep experience from through computing, teaching, leadership, and curriculum and assessment development. Rob, do you want to say a few words about your experience?
Yes, thanks, Nick. So this session we're going to be talking about today is the culmination of years with the work around project-based learning and physical computing, and should hopefully be inspiring, engaging you to try physical computing and project-based learning with your learners, either over the course of a lesson, over the course of a day. My background is, as Nick says, very much around computer science education, formal curriculum development through various UK-based and international exam boards, and obviously looking after the apprenticeship program, which is adult education programs at ARM.
Thanks, Rob. Yeah, so you're very much in safe hands, in Rob's hands. He's sort of spent a large part of his career dealing with these sorts of things and running CPD and thinking about the effective methodologies for delivering computer science as the subject has developed within the curriculum in the classroom. So the ARM School program, we are a program that is really focused on everything that goes from kindergarten up to the end of up to pre-university. And the way that we work is we support communities of practice of teachers with resources, which includes curriculum linked courses and projects, which you can access through our website, school.arm.com. And all of the projects that are referred to within this session and the previous 6 can all be found in the courses on our site. So I would encourage you to visit it if you haven't already and explore the materials. And this goes from project books, which look like this one on learning computing with the microbit, all the way to full courses that can last, a half a term or a full term. So it's worth, really is worth spending some time exploring the resources which are there. If you go to our website, you will find at the top of the page a link to our brochure, which really does describe everything that the school program offers to teachers. So if you're wondering about the sort of end-to-end offer that ARM provides in terms of support for teachers and learners in the classroom, that is a great starting point. It includes links to all the courses and explains what they cover and goes into some detail around the kind of underlying pedagogy and thinking behind our program, and that's what it looks like. So yeah, do spend some time looking through that if you can. At the bottom of that page, so this is school.arm.com, you can sign up for our school program newsletter, and this is once every 4 months or so. We send a newsletter where you can get the latest information on updates to resources, events, and other things that we're working on as a program. So it's very simple. Pop your email address in the box and click subscribe, and you can get those updates through to your inbox. Now, this series of webinars, all the way from 1 through to 6, and then today's event, which is number 7, are all based on themes connected with project-based learning and physical computing. And if any of this is of interest to you, if a particular area has sparked your interest and you'd like to explore it further, we would really recommend going to and visiting our online free-to-access professional development for teachers. So these 4 courses unpack a lot of the themes and topics that we've covered over the course of the webinar series. So simply visit edX.org, search for project-based learning, and our program Teaching with Physical Computing will come up, and you can start with Introduction to Project-Based Learning. It's free to enroll, and as I say, it does provide you with quite a lot of detail and opportunities to implement these ideas within the classroom. Now, this is the last session, as I mentioned at the top of the event. We started in September. We're finishing today. We started with Get Started with Physical Computing today. As Rob mentioned, it's all about bringing together the ideas that he's covered in the past 6 sessions and implementing them in a really engaging competition for students, which yeah, we've run a few of these as a program just to see how they would work, and to learn and to iterate the resources that we provide alongside them. Yeah, they've proven really successful. So we hope that this will inspire you to organize your own innovation day along the same lines. Now, the projects and the context for innovation days that that Rob will talk through in this session will be available online in due course. So we'll provide details of this within the email that we send out after the session, which will include a link to the PowerPoint deck. It will include a link to your certificate and a link to the recording of this session. So we will include within that a short explanation of how you can access those resources. So it will hopefully we can organize that within the next week or so, or within the next few weeks, so that you can download those materials and get started on planning your innovation day. Okay, so I think that is the introductory session covered. The main training will last a little bit over an hour, and then we will go into Q&A, and then finish off perhaps within an hour and a half from where we are now. I would also mention that one of the things that we've experienced over the past 6 sessions is that some people do, as the training progresses, they do experience some issues with sound and visual quality. I would just ask you to bear with us if that happens. This is often connected to the connectivity on the viewer side. So if you give it a couple of minutes, it usually sorts itself out and improves. So yeah, please do be patient if you experience those issues. Okay, so I will just finally say just a reminder that your certificate will be emailed out to you after the event. So that's how you get hold of that. And now we will get started on the main session. Okay, over to Rob.
Hello and welcome to the ARMscore program's How to Run an Innovation Day. This is the last in our current series of project-based learning and physical computing sessions, and culminating in how to run one of our exciting Innovation Day projects. So what are we going to be looking at in today's session? So we'll be exploring what an Innovation Day is, how it relates to the ARMscore program pedagogical approach, how to resource it, how to deliver it effectively, and all of the different things you need to consider when planning for delivering an Innovation Day to make sure that all things go well. We'll be looking at some of the pedagogical elements which we've been exploring over the past few sessions, and how they need to be tweaked or applied to fit the sort of the long form of a full Innovation Day. We'll also be looking at some of the logistical elements surrounding an Innovation Day, which is similar to a normal project-based learning project in a classroom, but just on a much bigger scale, and some of the things you need to consider and think about when setting things up as well. We'll also be looking at how you assess the day and how to capitalize on the success over the course of the project. So what is an Innovation Day? So the idea of an Innovation Day is a full day collapsed timetable project-based learning competition, and this is where you take one of the ARMscore program projects, or you can create your own, and you give students a set of tasks or success criteria which they attack over the course of a day and work collaboratively in teams to meet all of the success criteria. And typically these are quite large scale projects, and obviously they are tempered to the student's age and ability, but they are quite beefy projects where they have to both program an artifact as well as building an artifact which solves a specific problem. The ARM School program projects typically revolve around the global goals, so they have something around sustainability, and they're typically something which students can relate to and engage with, which is solving a sort of a real problem. A lot of the projects that we design are based around the microbit, although you can use other hardware and development boards as well. You can judge these competitions, so there is an element of competition. You don't need to have the competitive element, but as they're working in teams and they are creating solutions to a set list of objectives, that does give the opportunity to at least assess what the students are doing, but also judging if you were to add in that competitive element, and you can judge them on the outcomes of their projects, of the hardware, of the build, of the programming competency, but also around how they've expressed Fulham 6Cs, the greatest professionalism, creativity and innovation, because there's lots of different things that we're asking them to do as part of this, which try to move beyond just STEM skills, but also around communication, collaboration, creativity, innovation, and those sorts of things as well. And a big part of this is, which we try to build into all of our projects, is this concept of an elevator pitch. So a 2-minute presentation where students have to summarize their solution, how they've met the success criteria, how they've solved the problem, and be able to communicate that succinctly within 2 minutes. The idea is that you have 2 minutes in an elevator with somebody to sell your idea, and so they have to be able to do it concisely and also be convincing. So that's a big part of this, and that's something they have to think about as they're developing their project. So in terms of the project structure and the pedagogical approach, now the resources and the sort of templates that we provide as part of the ARM School program use the typical ARM School program schema, which I've gone through in detail in other talks as part of this series. But essentially we have setting the scene, which is the context where we lay out the problem, we lay out which global goal the problem relates to. We also set out what the large scale problem is there, and hopefully this is something that can hook learners in and will engage them. And then we lay out the success criteria, and this is sort of the crux of the whole problem really. And this is a list of objectives which the students need to meet, and this is what they're assessed against as well. And these build in complexity, and we'll show some examples of these for Innovation Days a bit later on, because you need to add in quite a lot of these to keep students engaged and busy throughout the entire day. And the next part of that is also the scaffolded support material. So this is not always needed. This really depends on the ability and age range of your students. Younger students may need a lot more support and a lot more hand-holding than older students, but the more complex challenge you give them, the more likelihood is that they will need some support material. But it's just a case of balancing it so that you don't give them the solutions. Stretch tasks are very similar to success criteria insofar as they add on additional complexity to the base success criteria, and it allows you to stretch your more able and more vigorous students whilst keeping them on the task and on track, so that you're getting a deeper understanding of the problem set and solution rather than teaching them something completely different. And then the final thoughts is sort of a wrap up at the end of the day where you reflect upon what they've learned and what they've created and how far they've come over the course of the day. Because what we find with these projects is that students get an awful lot done. They start with nothing. They start with a blank bit of paper and a few development boards and some wires, and end up creating something quite substantial and typically something relatively advanced given their previous experience and abilities. So it's a way of them reflecting on what they've actually achieved and what they've learned and all of the obstacles that they've overcome over the course of the day. A couple of the core structures to this as well, which is really important to get right, is get them to design their project before they build it. The temptation with this is that they're in a room, they're in a team, they're sat on a table with a laptop and they've got scissors and pens and cardboard and glue guns and all this sort of stuff, and they just sort of jump straight in and start building. And this it's a bit of a folly. They need to design what they're going to do beforehand, and this is a crucial part of how we assess this project as well, because we're not expecting students to come up with a perfect design straight away. but we do expect them to think up front about not just what their product will look like, but also about how it will work. We expect them to look at the inputs, the processes and the outputs. We think almost algorithmically at this point, start to decompose the problem and think about how they're going to solve the success criteria. And again, we'll look at some examples of this shortly, but we do want them to design this, and then as they are developing this physically and developing the code, then they will improve on it iteratively. And this is a key part of not just computing but all STEM subjects. It's this idea of sort of continuous improvement, continuous delivery, and always looking back also to the success criteria, making sure that what they're doing, what they're developing, what they're delivering is in line with the success criteria and isn't just something random that they've made up. We've all seen students when they're working on projects want to add in bells and whistles and additional functionality, which is nice to have, is exciting, but is not necessarily pushing them towards the solution. So it's really important that we keep bringing them back on track and referring them to the success criteria. And in order for them to do this, they need to collaborate. This is a team activity. They need to be working in groups of 3s and 4s. And in the larger scale projects, they are given enough projects so for each person can have their own bit of work to do, and they need to collaborate to be successful. And these projects are designed in order to do that. For example, the person doing the elevator pitch needs to be speaking to the person doing the coding and the person doing the building of the artifact itself, because they need to be able to explain succinctly what's going on. And the computer scientist needs to be speaking to the engineer in order for them to make sure that the development boards that they're programming will fit inside the artifact body, and that it's taking the sufficient input and doing something logical with that and giving a sufficient output to meet the success criteria. So they all need to be speaking to each other as well. And also the branding needs to work with the success criteria and what they're trying to achieve. We also have this idea of bonus missions, and this is sort of another version of like a stretch task where you give them additional things which are nice to have, and this might revolve around marketing and social media, even around what the product could do. So you might ask them to do, for example, videos for YouTube or for TikTok, and you also might get them to create a website or a flyer or a poster or something similar to that, bringing in some of those creativity skills and getting them to flex their branding muscles. So not only do they have to design the brand, but also utilize that brand in a sort of a marketing campaign. It's treating this entire project as a rapid prototype for a product, essentially. So a bit like what some engineers may do. They have a problem, they want to solve it, they have to productize it, and they have to put it into a format which is understandable to the general public. And doing all of this at once takes a lot of people. So they'll have 3 or 4 people to cover all of those tasks, and they have to do them in the right order. So that takes a bit of not just communication but also organization. So they have to be speaking to each other, and these are exactly the sorts of skills that we're trying to foster through this pedagogical approach. So we should have seen this diagram before, and I've laboured this in previous sessions, but these are all the different elements that make up project-based learning and practical computing, and we'll see all of these elements expressed through the projects that we're getting them to do. So starting at the top left, so we've got the hardware. Now these projects will involve some sort of development board, so there is some hardware involved, and they'll have to make that board fit inside a body of sorts. Now the different projects have different types of body, and we'll see examples of those later, but there is a making element to this, and so there's electronics hardware as well as sort of physical hardware, and those two things have to marry together and be robust in order to create a product which is will stand the test or the test of time. They also have to think about input, process and output. So this is that engineering mindset, thinking about how they can take inputs which are digital and then do something logical with those and have a sufficient output to meet the success criteria, and they have to be able to make all of that work as a product. So that bit there is the sort of the physicality of it, of those boxes in blue. The bits in green, it's all of this is project based, so they're given this criteria that they need to marry up to. These projects are also aligned to the curriculum, so all of the skills that they'll be expecting to express and the computational constructs that they'll be using to solve the computational elements of the problem are all pitched and aligned to most formal curriculums in most countries. So they'll be using all of the typical computing structures to solve these problems. They also, we try to make these as engaging as possible. Now, the engagement and contextualization is a very hot topic in project-based learning, and obviously you can make your own projects to suit local context. But as long as it's something which is engaging and relevant to your learners, that's the real important thing. And as long as the problem that they're trying to solve is real, that's really important. It's got to be something that students can see is changing the world, and that's why the global goals are a really good set of problems, because it allows students to see they're actually making a difference, and rather than it being some sort of abstract task that they can't really get their teeth into and really see it making a difference. In terms of sort of the theoretical side as well, by making an artifact, it's realizing how this program is touching the real world. One problem with learning computer science and learning programming more generally is that there are lots and lots of exercises, which is, create a function which does X and spits out Y. When that doesn't really seem useful to anybody, you don't really see it making a difference in the real world. And by getting students to take physical inputs, be it a temperature sensor reading, a light sensor reading, movement, and then doing some sort of calculation on that, then they're applying computational techniques such as logic, using selection, using iteration, maybe even functions. And so they're applying these computational constructs intuitively, and also in a way that actually solves a problem, so it's meaningful. And then there'll be some sort of output as well, so it's be it a motor moving or some sort of display on the screen, or it may be a noise. It really closes that loop of real world application and computational constructs, and that makes it really sticky in the student's mind, and then that really helps them learn how to apply these things, how to apply these techniques meaningfully, and it makes learning programming much more easy. And in through designing and developing their projects, they've been designing them from the get-go. They've been creative in how they're coming up with their ideas of creating their project and product, given the constraints placed upon them as part of the project. So it might be a constraint around resources, it might be a constraint around additional peripherals or sensors or other electronic components. So they have to be creative in how they deal with their supplies as well. And as I mentioned before, they're demonstrating full on 6 C's in terms of collaboration, communication, and that sort of thing. So they have to work collaboratively to make these things work. So that's the sort of the big picture, the big schema of how physical computing and project-based learning kind of fit together in these projects. So as I mentioned in the previous slide, these are Fulham's 6 C's, and these are the soft skills which underpin all of physical computing, but also are expressed in droves during these innovation days. So students have to demonstrate character, creativity, and citizenship to be able to solve these problems. They have to collaborate and they have to communicate, and they have to think critically to solve these problems. And this is all alongside the engineering skills and the engineering mindset. They have to demonstrate to be able to take this set of problems and develop an actual physical artifact to solve these, as well as all of the computational thinking skills through the programming. So all three sets of those really make up sort of 21st century skills of being able to think, do, communicate, and be critical in doing so, and also whilst also being creative. And all of these skills are really, really important. And it also gives us a foundation of things that we can assess as part of this framework. So to sort of loop this back to sort of computer science and the programming elements of this, as I mentioned, all of the students have to be taught to think systematically. So thinking about what the digital inputs are, or analog inputs as well, and also how those inputs are processed. What is it done on a sort of a functional level? Is it threshold based? How are they taking that data? What are they doing with that data? How are they processing it logically? And then what does that mean in terms of output? And this is really important with some of the projects that we'll look at a bit later, because they have to think really, really cleverly about how they are sampling their inputs and how they're processing it and what that actually means. And output doesn't necessarily need to be like a speaker noise or a motor. It could just be storing data in a particular format in a particular way. So there's lots of ways that this can be expressed, but the processing bit is where the computer science really comes in, where they have to take this raw input and think about how is it going to be sequenced, how can you use selection iteration to do something meaningful and useful with this, how can they apply Boolean logic, and how can they make sure that they are sensing multiple inputs at once, and how these things are processed, how that control flow is designed so that it works time and time again. And this is again falls into this this idea of iterative development, so that they can test this stuff and make sure it all works programmatically. And so I've already mentioned the IPO model, but this is fundamental to innovation days. They need to understand that no matter what the problem set is, that there are going to be some inputs and there are going to be some outputs, and these things have to be processed logically. And explaining this to students and even giving them templates with IPO on there for them to think about this is really, really useful. So getting them to think programmatically and decomposing the problems that you give them using this model is very, very, very helpful. And once they've done it once, it's relatively straightforward. But then when you give them more complex projects, they need to think about how many different types of input are there, and also how do these inputs potentially how they can get mixed up, how they may interact with each other. So there's an awful lot of complexity that you can get into very, very early on if they don't think about it in a decomposed fashion and think about these things individually. And this feeds really, really nicely into the sort of the design thinking element of this, because it allows them to, it gives them a model to break down these abstract concepts into something that they can then create a solution for. And this leads us to the design thinking. So these are the templates that we provide students typically as part of this, and you can see there on the left we've got an IPO table, so they will think about specifically what input that they will take, and that could be like a temperature, light sensor, or gyroscopic sensor reading, as it can be almost anything. Think about how they're going to process it, and also what will that mean in terms of output. And this helps them to break down what the success criteria is and design how that will work. And that doesn't necessarily mean this will tell them straight away what blocks to use or what code to implement, but it gives them a good model for them to model the real world, and it takes them a step closer to having a programmatic solution. And then on the right there, we've got a slightly more complicated design sheet there where they can start to think about the branding, what this thing will look like. They can sketch out their design. It allows them to capture what their objectives are, what materials they've got to think about, what the success criteria is, and any problems that they might have. And this allows them to constantly refer back to this design and tweak it as they go on. And ideally, students will start with one design. It will evolve and adapt over time. And the more students do this, they will get better at designing their solutions, and they're able to look at success criteria and design something which will be functional at least at the very beginning. But students initially struggle with this, and they struggle to conceptualize what the success criteria is, and to design something which is sufficient to solve it. But the more practice they get at this, the better. And this is always a bit of an awkward step. Students don't like thinking up front and designing things first, but it's really important that we spend a good amount of time doing this before they jump into the project, but also not laboring it. You wouldn't, in a full day, you wouldn't want to spend more than perhaps 30 to 45 minutes on this, because the students do want to get into actually building and making this. But this draws a line in the sand, if you will, allows them to get some ideas on paper, and then they can refer back to that during the making session, and it allows you to see how their ideas and their solution have progressed, which again gives us a really useful assessment tool to see how they've moved throughout the course of the day. And this is this idea of iterative development, and students are doing this naturally all the time. You're giving them success criteria, they're planning it, they're developing it, they're testing it, and then they're constantly evaluating it. And again, I've gone through this in detail in previous sessions, but it's just reinforcing this idea that students will be going through this throughout the course of the day. And I often get asked this, like, is the making part of this really, really important? Like, why do we need to get them cutting and sticking and making them? Because it can create mess. You get bits of paper and card and glue stuck to everything, and students are generally like to leave a mess behind them. But that's all part of the process. It's by creating something, by making something, they are physically instantiating their computational thinking ideas and designs, and that link between, as I mentioned before, it's that realization of seeing that code in the real world, and that really, really is important for them to see that happen, and it makes those algorithms and those computational constructs come real. And also understanding some of the engineering elements there as well around structure, robustness, material choice, material design, and working under constraints depending on what materials you give them. Working with paper and, like, for example, microbits, the paper has to be able to support the microbit, and that in itself is an engineering problem. So they have to think about how they're going to shore up their designs. And we'll see some more technical examples of this a bit later on with some of the examples that we've got. So that's the sort of the pedagogical elements of an innovation day. And now we'll move on to some of the more logistical elements of how to set these things up. So let's just assume that you've chosen an Innovation Day challenge. Now, we'll go through some of the ARM Score program examples shortly, but let's say you have one in mind, or you've thought of one yourself, and let's have a look at what you need to prepare in advance of it. So you first of all, you'll need an IT suite, so you need a room with access to IT facilities. Now, they may be desktop computers or they may be laptops. Space is crucial here. You don't want to be cramming lots and lots of students into a room without space. It's a good idea if you can to do this in a school hall or in a larger room and have laptops on Wi-Fi if you can do that. Otherwise, a normal computing classroom will do. But just make sure that the groups have enough space to have room to work on a computer and also make their artifact, because there is going to be obviously cutting and sticking and stuff going on at the same time. So making sure that the IT facilities work, first of all, making sure that access to the programming interface is allowed, is unblocked. You wouldn't believe how many times we've run these sessions and MakeCode is blocked at the firewall and they can't get access to it, and also that the USB ports have been turned off as well, which a lot of schools do for security reasons. And obviously you need the USB ports to function so that you can get code from MakeCode from the IDE onto the microbit. So that's just a practical thing which may seem obvious, but you'd be surprised how many teachers forget about this, and then things can go wrong on the day. So test this stuff as well. Don't just assume it works. We've all had a situation where a technician has said they've done something and then on the day it turns out it doesn't work for one reason or another. So it's worth making sure that you take a microbit, you write a simple program, and you make sure that you can flash the microbit from a student account, because obviously teacher accounts have got different permissions to student accounts. So get a test account from your technicians and make sure that this actually works, because if you can't get code from the browser to the microbit, everything falls apart and it doesn't work. So make sure that it's there. Also, more obviously, make sure that the hardware that you require turns up in time. If you're ordering stuff in from different suppliers, that stuff that can take time. Deliveries can be delayed, and all of this. So being prepared in advance is crucial, and making sure that you've got enough of all of the making elements that you'll need. For example, scissors, card, colouring pencils, tape, glue, all of this sort of stuff. These are all things that you need to make sure you've got access to. And with some of the more complicated projects, you might need something a bit more sophisticated, which it may be worth speaking to your design and technology colleagues for. For example, you may want balsa wood, you may want staplers, you may want glue guns, that sort of thing. So things that involve a little bit more D&T knowledge, and so it's worth collaborating with some of our colleagues to make sure that we can facilitate the making of the artifacts beyond just paper and sellotape and the like. It's also worth having spares of everything. I always find that there's always at least one microbit in a pack that doesn't work or won't let you get past the calibration steps. So do bear in mind that you do sometimes get dead on arrival elements, particularly with batteries. If the battery packs in the microbit packs have been sat in a cupboard or a shelf or in a warehouse for a while, in a cold room, they won't work anymore, or they'll be dead. So have spare batteries. Having batteries is really important, because whilst the microbits can take power from the USB port, the cables that come with them are only a couple of centimeters long, and so it doesn't really allow you to be very physical with the physical computing devices if it's tethered to a PC. And so having the battery pack allows them to move these things around, and as you'll see in the examples of the projects we have later, that is a crucial part of it, especially with the oil spill cleaner upper and the microsat projects. It's also really important to make sure that you have all of those things ready to go beforehand, and that you have enough for all the students, because you don't want them to be short. And also consider briefing your colleagues, because whilst you don't need a lot of people to facilitate these days, you can, for example, with small groups of up to like 30, you probably do this on your own, and I've done this many times, because the students largely will be in their group, they'll be working collaboratively, and you just leave them to it, and you just intervene when necessary, and you may go around interrogating them on their projects. But if you've got larger groups over the course of a full day, it's worth briefing any colleagues that you're working with, for example, classroom assistants or your D&T colleagues, about what the pedagogical approach is, why the computing element is balanced with the making element, why the two things working synergistically is really, really important, explaining that you're not giving them the solutions to any of the problems and that sort of thing. It's like only intervene where necessary, and don't spoon feed them. Also, things like planning the timings for the day. This can be quite flexible. It depends on the ability of your students, how quickly they'll get through the various elements, and it also depends on your school day, planning it around breaks and lunches and bus pickups and all that sort of stuff. It's that's quite a fluid element of the innovation day. Also thinking about power. One thing when you're using laptops is often laptop batteries can die, and it's making sure that you have power accessible throughout the course of this, and making sure, for example, like power cables are taped down so that people aren't tripping over things. So there's a health and safety element to this, and making sure that there's space on the tables for both the laptops, power packs, and all the making accessories. And if you have Wi-Fi, making sure that you have access to that Wi-Fi, so that you can get access to the IDEs. And the accounts, obviously the login accounts. These are all the sorts of things that, in my experience, typically go wrong during innovation days, and it's always the sort of the technical bits that can take a bit of running around. And there's nothing worse than starting an innovation day, getting the students really excited about the task at hand, and then they try and log in and they can't, or the Wi-Fi doesn't work, or they can't get the code onto the microbits. It just disengages learners, it derails the project, and it can take quite a bit of time to fix sometimes, especially if it's the same problem for all learners, and they'll be sat there twiddling their thumbs when the technician is trying to unblock a website, for example. Thankfully, because you're throwing them in straight away into the design element of this, then there is a bit of sort of pen and paper exercises that they can be doing if the technicians do need to do anything. And this is why it's a good idea as well, is that if you're using brand new microbits, is when you first plug in a new microbit, it has to go through a calibration sequence, and getting the students to do that first, and then do a quick test program, first of all, to make sure that they know how to get the code from the browser into the microbit, and also just to test that it works, and then they can start the design process for the challenge, and that way that everything works, and then they can draw everything up and then come back to programming it a bit later on. So that's a nice step in case anything does go wrong. And when you're speaking to colleagues as well, one of the things that you'll be spending a bit of time doing is explain to students what the features of the microbit, or whichever hardware device you're using, is. Students may not have used microbits before, they may not be familiar with the different sensors or the different outputs, they may not be completely confident with how to program it as well, or what the process of flashing it is, particularly around if you're using peripherals like the control bit or the sense hats, or anything that which gives some additional functionality. And if you're doing something around data capture, it's showing the students what these additional blocks and these different tools do, and you can do a little tutorial at the very beginning to show that, or you can let them learn through playing with it. And if you're doing some of the more complex tasks like the microsat one, you may want to have a lesson on sort of simple encryption concepts beforehand, but that's not necessarily always necessary. One thing you might want to do is when briefing colleagues is getting them to have a go at the project themselves, so that, because they will typically trip over the same sorts of things that students will, and for example getting them used to what the error codes are, and also what to do when they see an error code, and then obviously googling what the error code means to diagnose what the problem is. And so it's really useful if colleagues do have a vague idea about how to program using MakeCode, and it's not particularly difficult, but it's if they don't have time, then it just makes them more useful to the students if they can help troubleshoot. Not that we want teachers to be solutioning for the students. The idea is that the students are doing this themselves, but it does help if they can troubleshoot effectively. So in terms of the running order of the day, typically you will start off with the intro session, and you will talk the students through what a microbit is if they've never seen one before, or just remind them what the key features are, particularly if you're using some of the some more complex additional peripherals, or different types of input, or if you're doing some data science, just reminding them how to do that, reminding them as well how to flash the microbit or whichever device that you're using, and also for example on a microbit you can use web USB to download straight to the microbit rather than having to copy and paste it. So just reminding them of that process can save an awful lot of time. And if you're giving them any other types of hardware, for example if you're using motors or extension boards, it's worth reminding them how those things plug together, how they work, and the sort of the basics of the electronics, and you can spend just a couple of minutes doing that. Then it's worth taking them through the challenge, explaining what the context of the challenge is, explaining to them what the success criteria is, and going through in detail what the success criteria is, giving them some tips and tricks, and also explain to them what the making resources are and what the constraints are, more importantly as well, because these are the things that they're going to be assessed upon. Introducing them also to the design and making elements of it, like the design tables, and explain to them that they can't start making until they've designed it, and go through that calibration process to test that everything works properly, then start the designing. And then that might take you all the way to lunchtime, for example, but maybe not. You may be able to whiz through that in just 10-15 minutes if your students are a bit more older, a bit more switched on. Then spending the bulk of the time on that building an iteration. So you want to have a good few hours, at least 2 hours on this, ideally more. And then you want a bit of time at the end where the students will, maybe in the last sort of 45 minutes, you'll have judges or one of the teachers going around and taking the elevator pitch from the students. So they get that 2 minutes to present their project, and you need to do that at the end of the day. And then you may have the same or different judges going around and assessing the students' finished product, and give a reasonable amount of time depending on how many teams there are for that. And the OMSchool program have got an assessment rubric which you can download and use to judge the students' work. And then obviously at the end of the day you want to wrap up, congratulate everybody, maybe even the best elevator pitch, get them to do it again to everybody else so they can show off, although that's not necessary, but you can wrap up the day and then reflect upon everything that you've gone through and what they've done, and point out some areas of success which the students have done. If you've seen a particularly innovative solution to one of the success criteria, talk through it, call it out as good practice and as excellence and innovation. So I keep mentioning microbits in terms of this and these projects, but obviously other development boards exist. You have Arduinos, Raspberry Pis, and Crumbles as well. There's lots and lots of different development boards which you may have access to. Most of the projects that we talk about for the innovation days are microbit based, but you could switch in and out any of these products to do the days. You just have to make sure that you factor in the additional complexity that these introduce, such as the need for breadboards, header wires, additional peripherals. Not all of these boards are equal in terms of what inputs and outputs that they have. So just bear that in mind. You need to factor that into the process. The microbits is just an efficient way of doing this, and the projects have been designed around their inputs and outputs. But as I say, you can switch and interchange these products as you see fit. So when briefing colleagues, run them through what the structure of the day is and the rough timings so that they know what to expect, and make sure that they can G students along. Make sure that they understand the pedagogical model, as I mentioned before, making sure that they don't spoon feed the solutions to the students, and to use open questioning. It's really important that you brief teachers on, don't ask closed questions. Get them to explain what their algorithms do. If they're struggling with something, ask them questions about it until they can work out for themselves how to get around it. Certainly don't ever do anything for them. Get them to think about it. There's this brain buddy book boss sort of mentality where they need to think about the problem and try and work it out independently, demonstrating resilience, and then speak to their peers. This is a collaborative exercise. They shouldn't just have one student struggling independently. They can be working in their team, and if they need to, even working intra-team, so they can go and speak to other teams. One key thing about demonstrating gracious professionalism is that they can go and speak to other teams and see what they're working on and learn from each other. That's a really good way of demonstrating that. Another thing about colleagues is getting them to learn about error codes, how to troubleshoot, but that's not really an essential. But one thing is worth driving home is the focus on the success criteria. That is really, really crucial. Make sure that your colleagues and staff are aware of what the success criteria is and how it's being assessed, and that will allow them to support the learners more effectively, and allow them to implement and instantiate this pedagogical model in the most effective way. And the most important thing, and the thing where I think most people are lacking when delivering innovation days, is keeping the pace up. Students will naturally start quickly, then slow down very, very quickly, and then they'll realize that they're running out of time, and then ramp up the pace at the very end, and usually never quite get as far as what they want to. So it's important that all adults in the room are keeping up the pace and reminding students. You might think you've got 2 hours sounds like a long time, but you've got a lot to do, and you've got a lot of stuff that needs thinking about and working on, and usually iterating on multiple times. So yes, it's worth keeping the students motivated, engaged, and reminding them to keep looking at the success criteria and working at a rapid pace, because if they slow down, they will fall behind. Another element you might want to consider for making these innovation days more successful is involving external partners. Local businesses typically will be keen to engage with schools. They typically have corporate responsibility budgets, and they may even have staff that will volunteer their time to come and help with this sort of thing. And you may even be able to collaborate with them on using a context from their particular workplace and giving it a sort of career style element. One of the projects we're looking at later is all about space and satellites, and so you may have a local space agency that you could work with, and maybe even get an astronaut or somebody that works in space or satellite technology to come in and do a talk. They may want to introduce the project and read out the success criteria, and maybe even do a sort of a career talk as part of this, which helps meet the Gatsby standards in the UK, and it turns it into more than just a project day. It also enlivens the students and sees someone that works in this industry coming and speaking about why this sort of work is important. And alongside that, you may also want to speak to local press about getting some coverage about coming in and doing a nice piece on students working in STEM, working collaboratively to solve a real world problem and that sort of thing. That's a nice piece for the local press to celebrate. And you may be able to even ask these local companies for sponsorship, so maybe for prizes for the various elements of the competitive elements, or maybe even sponsoring for the hardware which is necessary for the day. So these are all things worth exploring, and it does take a little bit of time, but oftentimes these things reap rewards when you try to collaborate with external businesses. So I mentioned gracious professionalism previously, and if you've not come across this concept before, it's essentially full and 6 C's incarnate. It's this idea of, whilst this is a competitive environment and the students are competing against each other, they need to be doing so in a sort of a mutually beneficial way. They need to be working to solve the problems collectively, and they need to be working as fast as they can, whilst avoiding any negativity. We need to take away any conception of toxicity. We need to make sure that they, there is none of this kind of aggressive, toxic environment which often comes out in sports and that sort of thing. It's this idea of they are working, all pushing in the same direction, and they're all trying to express knowledge and theoretical elements through their physical products, whilst demonstrating empathy and good quality communication and collaboration. And that's difficult to get right, and I think even teachers can sometimes struggle with this as well. It's about being gracious through your application of your skills and knowledge, and this is something that we need to train students to do. It's about keeping it positive, keeping it holistic, and really treating everybody with due care and respect, and everybody trying to achieve something positive for positive outcomes. So that's the sort of all the kind of the hard and soft elements of what an Innovation Day conceptually is. We're now going to spend a bit of time looking at different examples of projects which you could use for Innovation Days. So the first one is the micropet. Now you may have seen this before in one of my previous talks, but this is essentially the simplest project which you can do, and I deliver a lot of these in both primary and secondary schools. And this is a nice short project which can be done in a couple of hours, but you could stretch it out to a full day if you had younger students, and this is typically done sort of primary age students. And the idea is that the students are making an interactive pet, and interactivity being the key feature there. So the context is there. You can see on the left is that students, loneliness is a real problem, and you need to create a digital pet that can be played with, and it must be interactive. And then you can see on there on the success criteria, it's got to be suitable as a pet, so it has to look friendly, and you can see some examples of what students thought about that at the bottom. It's got to be robust enough, so again, this is the engineering element. They have to make this out of something robust. You can see the examples there are paper, but you may want to give them card or wood or other stuff to make it out of as well. It must contain the microbit or the development board, and you can see from the smiley faces there and the heart there on the dog as well that that is the case. It must have a face and be able to express emotion. Now this is a really interesting feature of this, is that how do you get an inanimate object to express emotions through interaction? And that's quite a complicated problem. How do you can say, oh, a smiley face shows happiness, but what triggers that smiley face? Is it happy by default? Do you have to do something to it for it to be happy? Does anything make it sad? how do you take an interaction, and what is an interaction with a pet like this? There's lots of ways that interactions could be thought of, and this is really makes students think about how would they interact with the toy, and how is that input then taken? How is it thought about programmatically, and what would the output be? And a really simple example of this is imagine you had a pet, hamster or a puppy or something like that, and it might be the default mode might be happy. If you shook it vigorously, it would be sad. So how could you digitize that? So there is obviously an accelerometer and a gyroscopic sensor on the microbit. So the default state may have the happy face. It may sense up to 3G. And then if that threshold is reached, then it may then show a sad face, for example. So that's quite a simplistic example of how you could turn an interaction into an emotional response. And the challenge there is for students to unpack that further and create more interactions. So this is quite a simple project, but you can draw this out over more time by getting them to think of more complex interactions, and even having interactions between micropets. A really good example of this is the dog one that you can see there in the middle, and they actually had a second microbit which the grey bone there was stuck onto, and so they created a variable on the dog which represented hunger. It was like 0 to 10, and then in order to feed the dog, they had another microbit which the bone was on, and then the microbit with the bone had to be near the pet to feed it, and they used the radio blocks with a very low sensitivity, so that the bone had to be within about an inch of the dog for it to pick up the signal on the microbit, and then that would then increase that variable over time to feed it, if you will. And that was like quite a nice solution to that, to actually physically interact with the bone and the dog to make that hunger variable increase. And then when that hunger variable was low, it would have a sad face and it would be hungry, and it might make a hungry noise, because the version 2 microbits have a speaker on them, so you might be able to represent like the belly rumbling or something like that, or it might say that it's hungry. And so there's lots of ways to consider and conceptualize and implement interactions and emotion. So here's some of the other features for this particular pet. And as I say, you can get younger students just to have one or more of these types of interactions, and you can see there the feeding and the interacting ones I've already discussed. There may be other ones as well, using different types of sensors, such as the needing attention, and again having a variable that can decrement over time until you play with it, and it might use again the gyroscopic sensor, so it can sense when it's being moved or touched, and then that will increment that variable and keep it happy. Think of it a bit like a Tamagotchi, which some of us may have seen if you're of a particular age. It may have a sleeping and waking cycle, so it needs to sleep at certain times, and to put it to sleep the light sensor needs to be below a particular threshold, for example, and you can make it snore when it's asleep, for example. So there's lots and lots of things that you can play with around temperature sensors, and you can get them to talk to each other. The microbits also have a microphone on them, and I believe there is also some rudimentary sound recognition and artificial intelligence which you can implement on the microbits to recognize different noises and sounds and notes. So that might be worth exploring if you've got slightly more able or older students. So that's a very simple project for younger students, which you can take a full day. We're now going to investigate a couple of other projects which are slightly more complex and involve a bit more hands-on thinking. Now, all of the projects we're about to look at are based upon the global goals. The next one we're going to look at is the oil spill cleaner upper. That's based upon goal 14, so life below water. But I just wanted to dwell on this for a second, that if you are coming up with your own projects for project-based learning activities, these are a really rich source of ideas for you to base your projects on, and they are very real, and students can really sink their teeth into these and really see how their solutions are making a difference in the real world. So the oil spill cleaner upper. Now this context will be something that students should be already familiar with. Oil spills do occur occasionally. They are incredibly damaging to the local ecosystem. And what we're going to get them to do is to develop an autonomous boat drone, which will drag some smart material that mops up the oil. And this is using a smart material which is real. This is actually a real product. I mean, getting hold of that smart material may be very difficult. I think it's a proprietary bit of material, but you can simulate this using a sponge. And then these autonomous boat drones are real. You can see there in the bottom left there is an actual picture of a real one, and students are going to model this solution and make their own floating boat drone. And you can see an example of a microbit in a boat drone there in the middle. And the success criteria is that it needs to float, and it needs to start with the press of a button, and it's got to navigate autonomously over an area. So hopefully that will get your algorithmic ideas, juices flowing, because it needs to be, first of all, able to float, and then it needs to be able to mop up an oil spill following an algorithm. And the idea is that there would be a swarm of these. So I'm sure you can start to think about the other things that they would need to think about for this to work as a swarm. So that's the sort of the context and the idea. So just an example of how you get them to apply the design thinking elements to this. So this is an IPO table. As we know, one of the success criteria is that it needs to start at the press of a button. So the input is going to be a button press, which obviously microbits have on them. There will then be an algorithm. Now this will be, when you're implementing this, will be obviously much more complicated than just this diagram, but they'll have to have an algorithm which controls the motors so that it goes up, across, down, across, up, across, down, across where the oil spill would be. And so they need to think about how would they get the motors to perform like that, and also where would you put the motors in order to get it to be able, for it to be able to turn at 90-degree angles. So there's a few sub problems within that which they will need to decompose and think about how they're going to do it. And also, if you're testing this in real life, if you actually have a body of water or a paddling pool with these boat drones in, how does it deal with ambient conditions? Water isn't always flat. The sea is a bit wobbly. It has wind. So how would a boat drone deal with those ambient conditions? So there's an awful lot of things that you can unpack here, and you can simulate these things like by having like a fan or getting someone to sort of shake the water a little bit to see whether the algorithm still works if you add in these additional factors. There's also the engineering side of this, and so for example, students may be tempted to put a servo motor at the back with a propeller, and that will make it so that it can go forward, but it can't turn. So you need to introduce the idea of paddles, and how do you make the paddles work without having the motor in the water? So there's some design thinking that needs to occur there, and these have to be able to turn 90 degrees. So you have one paddle spinning while the other one not spinning, for example, and doing that for enough time that it will spin just 90 degrees and no more. So there's a lot of trial and error that goes on here, and this is back to that iterative design concept where they will try it for a couple of seconds first, realize that it spins around multiple times, and they only need to turn 90 degrees, and they have to start playing around with the speed of the motor and such like. So there's lots of different factors that they need to factor in when designing this. There's also stuff to think about in terms of the making elements. So to deal with motors, you may need an additional peripheral board, and you can see here there is an automation bit. Now there are lots and lots of different additional peripherals that allow you to control motors. I think this one is quite an old one now. I'm not sure if you can get this anymore, but there are newer versions of this, and it allows you to control multiple motors from a single microbit, and it sorts out all the voltage for you, and it allows you to control them digitally. There's also the engineering element of having the how do you attach the motors to the body of the boat, and there's kits that you can buy for that, or you can just give them tape and glue and that sort of thing, so they can make this stuff work. And again, this is why the battery packs are really, really important here, because you don't want to have the laptops floating in the water with the microbits. And it's obviously you might consider from a health and safety perspective about this is electronics, we don't want to get it wet, which is true, because getting these things wet will break them. Although the microbit only has a voltage of 3 volts, so no one's going to get hurt if this falls into the water. But just something to consider. You don't want to be losing microbits by getting them wet. And testing that the boats float without the electronics first is usually a good idea. And here's a little bit more of a close-up of what the finished solution for that looks like. You can see there's some header wires there. There's a diagram on how to plug them in. You can see this particular implementation has both motors running off the same 3-volt output. So this is this is an example of some of the scaffolding that you might give to learners to enable them to access this more quickly should they need to, or if they're really struggling with electronics. Some students may never have used electronics before in this way. They may not know that you need a positive and negative terminal. They may not understand what grounding is or what voltage is. So you can speed up that process if you don't want to cover the theory by giving them these cheat sheets to enable them to access that. And again, these are all accessible in the ARM School program material, but if you're designing your own, it's worth considering creating the scaffolding material should you need to. So that's the oil spill cleaner upper task. It's quite an exciting challenge. Students really like this, especially if you can get them to test it in a body of water. You might have a pond or a swimming pool or a paddling pool or something similar, which you can use to test this, and it means that they can keep coming back and testing their projects. And seeing this stuff work in real life is a really magical way of learning. And it's yes, it's seeing is believing with this type of pedagogical approach. So the last project I'm going to go through today is the microsat project. Now this is the most complicated one that we have so far, and you could really conceive of it as being 4 projects in one. Really, it's quite a complex one, and the idea is that this is sort of a large-scale project, and it weaves in a little bit more cross-curricular elements, because we bring in elements of physics into this as well. So, and this would typically be used with slightly older learners, maybe sort of 14 to 16, and maybe even older students as well, depending on how you want to arrange it. But the context is that you've been drafted in by a space agency, and you can contextualize this to whatever country or whichever space agency is relevant to your jurisdiction, and they've asked a team or your team to create a microsatellite, and there has been a coronal mass ejection, and you may get them to, in the lesson before, research what a coronal mass ejection is, and why that is a bad thing for planet Earth and the electronics on planet Earth. And then you can talk to them about what a microsatellite is, and you look at examples of that. And if you're using something like a Raspberry Pi, for example, for this, you can look at how Raspberry Pis have been sent to space and how there are lots of them on the European Space Station. And so there's an interesting sort of context there which spreads into other subjects. But there are 4 missions for this particular microsat, and the first one is measuring telemetry. So this is on when the satellite is coming back down to Earth, measuring the telemetry for that. The second one is all about encryption, and then the last one is there's a robotics project about cleaning up space debris, and then the last one is about about a collision detection system, and how space is a messy place, especially in orbit. And so how can it sense whether it's going to crash into something, and how can it avoid that? And then, as with the other missions, there are bonus missions as well. So there's the elevator pitch. We'd want students to create to open source their code. So we want them to store it on GitHub so that it's public. We'd also want them to create some social media around this using TikTok or YouTube Shorts or something like that, just short videos about their process and their team. And we see this utilized really successfully in like First Tech Robotics. So there is precedent for why this approach works. And also creating websites. This is where they can create a free website using Google Sites, and they can put on their branding and their explanation and effectively capture their elevator pitch in website form. So that's the big picture, and we'll go through each of the missions now and look at the success criteria and dig into some of the more technical elements of this. So mission 1 is that this is the building bit of it. They've actually got to make their satellite, and it's got to collect the telemetry on re-entry. And we also need a way to visualize that data, and that's a really, really important part of this. And we're going to simulate the telemetry gathering element by dropping the microsatellite from a height. So this is another thing you need to factor in for the preparation if you're going to do this project, is that you're going to be dropping something from about, say, 10 meters. So it may be out of a window, it may be off off a mezzanine or something like that, depending on where you've got access to in your school. And you may do this in physics lessons where you have to create a parachute for an egg or something similar. This is typical for for physics lessons, and so we're going to do something similar, but with the added benefit of we're going to be able to measure the telemetry using the microbit and log all that data in a CSV format, and we're able to see the effects of the different parachute configurations by looking at the data. So let's look at the success criteria then, because it's got to be rugged. That's the other part of it. It's got to be able to survive a drop. So first of all, they have to be able to build a microsatellite which is no bigger than 30 by 30, and 30 centimeter cubed effectively. And it's got to be able to hold 4 microbits and their batteries and their control bits, because each one of these missions uses a separate microbit to do something separate. So these are sort of subsystems within the microsatellite. It's also got to be branded, so it brings in that creative element to it. It's got to also have a suitable parachute, which will be able to take the weight of the microsat and slow it down effectively so that it doesn't break. And it's also got to be able to collect the data for 2 drops. So you're going to have to investigate how to capture data and log it on the microbit in order for them to do that, and how to create that visualization. And this is very easy to achieve with the microbit version 2, and there's inbuilt tools on the microbit to do that. And if you're not sure how to do that, then check out the version 2 micro course, where there is a project on there on how to do exactly this. And then they have to be able to explain what the data shows from their parachute. So they'll have two different types of parachute, maybe one with, maybe one without the parachute, and then they'll have to show how that what did they learn from that data, and they'll have to tell us what that data represents in real life. And that's an important scientific skill there for them, interpreting data and relating it to the real world. And if they're doing, for example, a good way to show this would be using the social media elements. So they could video the first drop, video the second drop, and then show the data, and then get them to explain, piece to camera, how that data represents what happened in that drop. So that'd be a really nice way of sort of mixing media and data analysis and data science together. And so that's quite an interesting challenge for students to do. And so that's the first mission, is to build and create the product, the artifact, and log some data and visualize it in a meaningful fashion. So the next one, this is the secret mission. So there is a damaged satellite. So this is where you have to create a separate satellite. And this is one of the things that the teachers could build as part of their preparation. And it's going to be transmitting an encrypted message. So this is where the encryption theory comes in. And the task is that the students need to have one of their microbits be able to sense the signal coming from this damaged satellite, and then be able to decipher it, or unencrypt it, if you will, and then present the findings out to a representative. So you might have one of the teachers sort of playing the part of the space agency, and then the students have to say, what does the message say? And so they're going to be interpreting what that cipher is. And you can use any type of encryption algorithm. It could be something like a Caesar cipher, for example, and the students just have to work out what that is. So you might want to tell them what frequency the microbit is transmitting on, and then it may be just a random collection of characters, numbers, and letters. Or it could be an anagram. It could be something different. You could make it more complicated if you want to. But there needs to be a separate microbit, which is in the form of a damaged satellite, which is transmitting that. And students, you'll get them to take turns to come up with their microbit to test whether they can first of all receive the data, and then what can they do with that data. So there's sort of two elements to it. There's the physical bit, and then there's the interpretation. And that could take them quite some time, depending on how complicated you make the encryption algorithm or the Caesar cipher, especially if you start to mix in special characters. So think about what that might be. And the message could be anything. It could be a password. It could be a message. There's lots of ways of making that interesting and fun. And whilst if students are fairly switched on, they may work this out relatively quickly, and you can have like a separate prize for the first team to work out what the message is. So the third mission. So as I mentioned before, this is all about space debris, and it's a lot of satellites can get damaged by debris in space, and it could be bits of rock, it could be bits of other satellites, it could be just waste left by the space stations and other satellites. And so the system, we need a way of being able to clear up space debris. So let's say that the microsatellite is flying near a piece of space junk. They need to be able to deploy something that can pick up this debris, and it can be triggered remotely. And so this is like a robotics project, basically. So it could be something like a robotic arm, or it could be a net which is deployed, which can catch something, and then it needs to use at least one motor. So it will be motorized, obviously, for the robotics element. And that's quite an open-ended challenge. And so you could have something like an empty can, like a kind of pop or whatever, for or some sort of soft drink, which could be the space debris. So that could be the test, is that you put it next to the satellite, and it has to be able to collect it and keep hold of it, and that will be whether they meet that success criteria or not. So there is an element of robotics there that they need to think quite carefully about, and how they will implement it. And again, this is where you can add in some engineering skills around resource scarcity. So you might only have two motors, you might only have a few bits of card or pulleys or whatever. So think carefully about how you would implement that. But that's quite an interesting challenge. And then last but not least, it's the collision detection system. So they have to think about how are they going to come up with a standard protocol for collision detection, because let's say you've got 10 different teams working on this. So that's 10 different ways of potentially finding out where other satellites are, and 10 different ways of communicating. So they have to have a representative from each team go and speak to the members of the other teams who are representing mission 4 and work out between them collectively how are they going to sense whether other microsatellites are within 1 meter of them, and then it has to play a warning sound when it's within 1 meter. So they have to think about how are they going to first of all detect that, how are they going to come up with a common way of sharing that information between the satellites, and how will they know which satellite is too close to the other satellites. And they also need to make sure that they're not interfering with each other as well. So this is quite a complex problem, because not only do they need to work collaboratively, they also need to agree on a protocol for detecting who's who and how do they identify each other, and what do they do with that information as well. So that's this is a really good example of like an open source style project, and we want them to obviously log all of this on GitHub. And then we want them all to them present. We want one or more of the candidates from the working group across all the different teams to be able to present what their solution is and how they've collaborated on this. And this is a really good example from the tech world of agreeing on standards. For example, agreeing on what 5G is, or agreeing on what USB is, and lots and lots of different companies and different stakeholders need to agree collectively what these physical and digital standards are for it to work across all these different devices. So this is a really nice industry style task. So you can see that those 4 missions are quite meaty in and of themselves, and this is why it's more suitable to older students. And for example, you could just take one of these missions and do an innovation day with it, or you could take all 4, whatever suits your students better. And in addition to those missions is the bonus missions, which I mentioned previously. They have to be able to do this elevator pitch, so a 2-minute one. They have to open source all of their code, make sure that it's in a presentable format, and make sure that it's commented and easy to read. And you may want to add in, as I mentioned before, this social media element and getting them to promote their solution and getting them to communicate it in an effective way, and letting them flex their branding muscles through both social media and also via the website. And again, these are all things that you can add in or take away depending on how much time you've got and how big the teams are. But there's enough work there with those bonus missions and the 4 missions there to keep a large team busy all day, and maybe even a number of days. So you can see that's an example of a more technical, complex project, and then the micropet is a more simplistic one as well. So there's some examples of some of the ARMSCORE program innovation days, which were tried and tested and work. But obviously you can also make your own. You can create your innovation day on any topic or theme that you see fit. You can use the ASP schema as a starting point. You can use the training material that we've put together here to help shape the project. As long as the context is suitable for your learners and you're confident that it will engage your learners, you can't really go wrong. But having properly structured success criteria is really important, and making sure that you build the complexity up and make sure that they're tailored to your learner's ability, and making sure that you stretch them appropriately as well. Don't make the projects too simple. I think looking at some of these projects, they seem on the surface to be really complicated, but they are eminently achievable. For example, like the oil spill cleaner upper challenge, we've done that with 13 and 14-year-olds, and they managed to successfully program that over the course of a day. And what seems like an insurmountable task is very, very achievable when they work hard together and they're prompted and given the appropriate scaffolding and support. They can achieve an awful lot. And again, don't forget to blend the making and the programming elements. This is a computational making project, but the engineering bits shouldn't be forgot about as well. And also, consider using cross-curricular activities. For example, like with the space, with the microsat task, with there's elements of physics in there, and you can use data science there to gather data for anything. You could use data science to measure acceleration in a physics lesson, or demonstrate gathering data for like a weather project for geography. So there's lots and lots of different ways to use data science effectively when creating your own innovation days. And please do use the ARMSCORE program material as a stimulus and inspiration for creating your own. And so all of this, sort of taking a step back now, is an example of project-based learning pedagogy. And you can see this quite complicated diagram here is all of the different facets, features, pedagogies, ideas, theories and strategies which make up project-based learning. And by running an innovation day, you'll be crossing many of these elements. And if you want to learn more about the sort of the theoretical underpinnings of project-based learning and physical computing and innovation days, then it's worth looking at unpacking all of these theories on the Armour Score program edX courses, and they're available free online and go into all of this detail in a lot of detail, and you can learn all about the theories that underpin this wonderful pedagogical approach. There's also all of the Armour Score program resources, which are available on school.arm.com. There's different teaching and learning resources there. There's the micro course book. There's different courses, lots of computational thinking challenges, and also with some YouTube videos about computing with microbit and with MicroPython. If you're interested in learning more, please do check out the courses. This session today has been taking material from course 4, so where we talk about innovation days in more depth, and we speak an awful lot in that course around gracious professionalism and the other areas that we touched on today. But if you want to learn more, please do check out the other 3 courses as well on edX.org and just search for project-based learning. And that's everything about innovation days. If you do create innovation days and you want to share them on social media, you can feel free to tag us in on socials and have fun enjoying these and enjoy using this amazing pedagogical approach to inspire and enthuse your learners. Thanks a lot.
Fabulous, thank you, Rob. Okay, before we move on to Q&A, I'd just like to hand over to our colleague Surya, who will talk briefly about the feedback form.
Thank you, Nick. Good evening all. I have shared the feedback form link in the chat window. I request all the participants to give their valuable feedback over there.
Excellent, thanks, Surya. So you should be able to see in the chat there, as Surya mentions, a link to the feedback form. So I'd be very grateful if you could take a minute or two to complete that. We do look at all the feedback and consider that for future sessions. Okay, so let's move on to Q&A. So just a few questions that have come in, which I think perhaps for the first one, Rob, I can direct this at you, which is a fair point. So is it a lot of work to organize an innovation day? And I think expanding on that, I would say, what should a teacher consider in terms of their the amount of time it's going to take out of their day over a period of weeks of planning, etc., before embarking on organizing one?
Well, doing a full day activity with a class or a year group or a cohort is always going to be a little bit above and beyond a typical lesson. But doing an innovation day with physical computing and hardware does take a bit more prep, but maybe just something slightly out of the ordinary. It depends on really your experience and expertise with the hardware. If you have the resources available to you, then it's not that much extra work, because you can take the projects off the shelf effectively from the Armour Score program's resources, and then as long as you've got the hardware and the facilities around the IT infrastructure and the making materials, then it's relatively straightforward to implement. It's just a case of just running the session as is planned out in the documentation. If you're designing something from scratch, then that takes a little bit more work, a little bit more thinking about. But it's mainly logistics. It's like the complexity of the project is one thing, which we've tried to remove by providing examples of these innovation days. It's more organizing the time, the space, the equipment, the hardware, the staff, that sort of stuff, which you can't avoid with this type of project. And if doing something large like an innovation day seems too challenging, then perhaps experiment with implementing physical computing or project-based learning in a more simpler fashion by doing it in a single lesson. And again, we have lots of examples of resources for that as well in the Armour Score program corpus of resources. So start small, and then when you're feeling confident with the approach, then jump into something a bit more meaty like an innovation day.
Yeah, I think that sounds like great advice, and I think it relates to this the second question, which I think you covered fairly extensively on one of the slides within the presentation, which is, having run an innovation day yourself, what's the main advice you'd give to someone to make sure it's well prepared? So you talked about needing to make sure that the make code was unblocked, that the laptops were all charged and working, and all of this sort of stuff. There is quite a long list of things that you need to make sure are in place so that you don't trip up on the day and kind of spend time troubleshooting on the technical side of things.
Absolutely. I think the most important thing is to test the process from end to end, and particularly if you're using a microbit, make sure that you have an account logged in as a student using on a student account. So work with your technicians, get a microbit, plug it in, chuck a bit of code on it, make sure that you can program the devices and that they work. The physical element's a lot simpler, obviously, because you just need to give them the resources. But from the technical side of things, make sure that that end-to-end process of getting code onto the devices does work for the students, because that will really make it will derail the activity if you don't do that. The other activity is making sure that you keep the pace up, and this is, it seems unfamiliar with teachers when they first start doing this, is because students start very, very busily, and then they get excited, but it's about keeping them engaged and keeping them on track, because there is an awful lot of stuff to get through, and you have to crack the whip, if you will, to make sure that they do finish it in time. You have to keep them driven, because the pace tends to slow down in the middle and then picks up towards the end, and then students can sometimes feel disappointed if they don't complete the activity, even though they had enough time to. So keeping the cadence high, going around and using your time to interrogate the students, ask them why they're doing what they're doing, get them to explain their code, explain how their solution matches their design, that sort of thing. So, really teasing out the information. You can use that to do some informal assessment at the same time, but just making sure you're using your time constructively and keeping everybody engaged and on track.
And one of the things we've talked about actually within the context of project-based learning generally is that if you've got a team of students working on a problem, typically from the outset, they will often go towards the task if they're allocating tasks within the team that they feel most comfortable with. So if they're, some students might go towards, naturally gravitate towards the more the marketing piece and developing logos, etc. Others who may be more familiar with programming might sort of take the lead on that. Would you recommend within the course of a innovation day swapping those roles, or do you think there's just sort of it's difficult to shake those things up in a time pressured environment?
It really depends on the project. I mean, a lot of the projects involve it forces the students to not just take a single role. You wouldn't get very far with the more complex projects if you just had one student doing the coding and the other one just doing the logos, because there needs to be this joined up thinking from the design through to the implementation. And for example, like the student that's doing the elevator pitch, for example, needs to be able to explain what the code is, and needs to be able to explain the design decisions. And the students that's coding needs to be working closely with the engineering leads so that their solution matches the body of the project. So the projects have been designed so that it forces collaboration, so that they can't just work in silos. I mean, you could, if you notice your students just sort of siloing off and only working on one thing, you could swap them around. You can give them different roles. So you could say you've got a marketing lead, an engineering lead, a programming lead, and you could force them to swap around. But they shouldn't need to over the course of the project, and they will naturally go to projects or to work which they are best suited to. But we do want to give all the students an equitable access to the experience, and we want them to collaborate so that they all understand what's going on, both in the code and how they are solutioning the problem that they've been given.
Great. So there is a final question, which I think I'd like to use as a jumping off point to a related question. So a question about the how this relates to the India's national education policy. Well, just up front, I think the people who've joined this webinar will be more familiar with that policy than we are. But I note from looking at it, it talks about experiential learning. It talks about holistic development of the learner. It states that learning should be holistic, integrated, enjoyable, and engaging. And it also discusses the use and integration of technology. So I think all of those things, hopefully you can see actually through the past 7 sessions now, really are brought to the fore through the use of physical computing and project-based learning. But I think it does lead an interesting question in terms of implementing these sorts of things within your school. Rob mentioned that today's session links derives from some of the topics that are covered within this 4th training course within our Teaching with Physical Computing edX program. And within that, we talk about stakeholders and ensuring that you've got, how do you get people on board within your school for taking what may be a very new approach to teaching and learning as part of your practice. So I think, Rob, I'd just like to ask you to reflect on that. What sort of advice would you give briefly to teachers in terms of engaging with groups like senior leadership?
So in terms of engaging with senior leadership, I think the first stumbling block would be convincing them of the efficacy of the pedagogical approach, because there is a resource cost to this in terms of time and organization, specifically about an innovation day, which is obviously slightly out of the ordinary in terms of normal delivery. But it's a case of letting them know or educating them about why project-based learning is a really useful pedagogical approach and how it can be quite impactful. And usually these sorts of things, it's show them through demonstration. So you might want to first of all start off by doing a single lesson and having a SLT member observe and see how students are learning in a different way. And they will be aware of these national policies around implementing different pedagogical approaches, which are demonstrated through these projects, and they will see the approach here, hands-on, and that should convince them as to why it's a useful way of learning. And whilst it can seem almost slightly abstract, just like and against a formal lesson around computer science or maths or something similar to that, this way of learning, whilst slightly more effort is involved in setting it up, is really, really impactful. And when once they're confident in the approach, then they'll be more happy to do something larger like an innovation day, which can really, really enthuse and engage your learners. But there is no getting away from the fact that it is slightly more resource intensive, but the results pay dividends in the long run.
Fantastic. Great. Okay, so that's the final question. We'll move on to closure. So it really just remains for me to thank CBSE for working with us over the past 6 to 9 months on this range of webinars. In particular, Dr. Saha and Mr. R.P. Singh. As mentioned earlier, at the top of the presentation, you can find recordings for all of the sessions on the community.arm.com webpage where you signed up for this session. So if you've missed any of them, you can dive in and watch previous recordings. The certificate will be sent out to you shortly. And if you are this is via email. If you're interested in any of the topics covered within the 7 sessions we've covered since September, then please do sign up to our free-to-access professional development program, Teaching with Physical Computing, on edX.org. You can explore these topics in greater depth. Okay, so thank you very much for joining us, and I hope you've enjoyed the session. Thank you very much.